Hello, my name is Paul Edmiston at the College of Worcester. The goal of this project, ER 18-1300, was the development of absorbents for perfluoro and polyfluoroalkyl substances from water. These compounds, generally referred to as PFAS, are often found in groundwater, and absorbents to remove them would be of very high use. The means to do this was to develop materials through rational design to best understand what characteristics are required to absorb PFAS. The materials we used to do this were organosilica compounds. Organosilica is prepared through individual precursors that are polycondensed to form resins. The ideal part of this is that the chemical identity of these precursors can be chosen so that they become incorporated within the absorbent particle. In this way, we can rationally understand how a specific type of chemical functionality leads to absorption. The type of organosilica resins that we use are called organically modified silica. These organosilica particles have the unique ability to swell upon absorption. The swelling is so great that the particle beads can actually grow 2 to 3 times in size as they absorb compounds. We study absorption using a variety of experiments, including absorption kinetics, absorption isotherms, lab-scale breakthrough curves, and a pilot test at the DoD site. What we found is that enhanced absorption occurs when there are first hydrophobic pores which PFAS can accumulate. However, it's important that these pores have cationic groups to help bind anionic PFAS compounds such as PFOA and PFOS. What we found was that PFAS actually aggregates within pores. In other words, it comes together to form macroaggregates and associates with itself. Thus, the unique ability of organically modified silica to swell was really useful in enhancing absorption capacity by being able to expand in size to accommodate this aggregation of PFAS compounds within the pores. This led to a very good absorption capacity. This could be demonstrated by the pilot test where we conducted an experiment using contaminated groundwater containing PFOS. It was found that 1 kilograms of SOMS was able to treat over 15,000 gallons of water containing PFOS prior to breakthrough, meeting EPA guidelines. An advantage of the materials that we made were also the fact that they could be regenerated through solvent rinse. This was done by taking the resin and rinsing it with a solvent like methanol, which causes the PFAS compounds to be completely liberated from the resin. Now this is very useful because then the absorbent can be reused again to treat water. However, another major advantage is that the methanol rinse, which now contains the PFAS compounds, can be disposed of in a proper way. The overall value of this research is that we better understand now how PFAS compounds absorb to resins like organosilica and similar types of materials. This can now be used as a roadmap to design low-cost remediation absorbents for use in treating groundwater or surface water. In the long term, we hope to reduce the cost of treatment to allow a wider application of absorbents for removing PFAS compounds, which is an important environmental challenge. Thank you.